Hello, and welcome to the first in our series of GTE Sylvania International Video Training Seminars. These seminars are designed to acquaint you with the world of lighting, to give you a basic understanding of one of the most important tools in modern life, the electric lamp. In this program, we'll be discussing the oldest and most familiar type of electric lighting, the incandescent lamp. Incandescent lamps are used in almost every situation where light is needed. They help to guide our way, make our whole world more beautiful, and keep us feeling safe and secure at home. There are over 500 varieties of incandescent lamps. Add in the different voltages, finishes, and bases, and the number expands to several thousand. But they all operate on the same basic principles. The original incandescent lamps were pioneered in 1879 by Thomas Edison in the United States and by Joseph Swan in England. They essentially had the same idea at the same time, enclosing a carbon filament inside a vacuum bottle. The vacuum prevented the carbon filament from burning up as it would have exposed to air. While the basic idea was sound, the carbon filament just wasn't practical. It produced little light, and it didn't last very long, and carbon filaments also broke easily. Then, in 1911, an American, Dr. William Coolidge, developed a method of making filaments from tungsten, which has the highest melting point of all metals. The result was a lamp that combined high output with long life and durability. Over the years, many refinements have been made, but in design and construction, incandescent lamps are still similar to the first Edison lamp created over a century ago. Before we examine that construction in close detail, we should define a few terms. For example, how much light does this lamp produce? 100 watts of light? No. The total amount of light produced by any lamp is measured in lumens. For example, a standard A-line lamp of 100 watts produces approximately 1,750 lumens of light. That's the amount of light being produced by the lamp. Now let's use that light to look at these books. Are there 1,750 lumens of light falling on this page? No, because lumen is only a measure of light at the source. The amount of light that's actually falling on this page, in fact, the intensity of light illuminating any particular area, is measured in lux or in foot candles. 10 lux are approximately equal to 1 foot candle. With a light meter, you can easily measure the illuminance of any area. The average office is between 500 and 1,000 lux. That's 50 to 100 foot candles. Remember, the light illuminating any area is affected by the lighting fixture, too. The same lamp will give you different results with different fixtures. Now let's move on to another important concept, the color quality of light. When a blacksmith pulls a piece of iron from a forge, it glows white hot. It incandesces. But as the smithy works with the iron, it cools, and its color changes from white hot to yellow to red, and finally back to its original black. At different temperatures, the light is a different color. In the same way, different lamps emit different colors of light depending on the composition of their filaments, the fill gas, and the temperature to which the filament is heated. If enough heat were applied and the metal didn't melt, the light emitted would go beyond white to blue. The human brain tries to perceive nearly white light sources as white. But the difference between color temperatures becomes obvious when they're mixed. Here, sunlight, the higher temperature light, appears blue in comparison to lamplight. In order to systemize the definition of color, the International Commission on Illumination, known as the CIE, developed a set of standards for light and its values. These standards are used by photographers, designers, lighting companies, anyone for whom knowing the value of a given light is critical to choices of films, fixtures, even interior decorations. This CIE color chart shows that when tungsten is heated, it begins to emit light, progressing from red to blue as the temperature goes higher. Color temperature is measured in degrees Kelvin, a temperature scale that makes it 0 degrees at 273 degrees below 0 centigrade, the point at which molecular motion stops. Most incandescent lamps emit light at about 2800 degrees Kelvin. That's right about here on the chart. You can see that it's a little bit yellowish, but when it's the only light source, it appears to the eye as white. These color temperature designations are applied to both artificial and natural light sources. Modern incandescent lamps are much more efficient than in Edison's day, but they're still one of the least efficient sources of light. When you turn on an incandescent lamp, 2% of the power is lost to lead wire conductance. 10% is lost to fill gas conductance and convection. 0.5% to ultraviolet, which is not visible and is absorbed by the glass envelope. 81% of the power is used to generate infrared, or heat. That means just 6.5% of the total power is actually used to produce visible light. Not very efficient. Since the construction of all incandescent lamps is basically the same, let's take an in-depth look at the construction of one of the most popular, the A-line. The heart of the lamp is the light-producing filament. As we said, tungsten is the best material for filaments because it combines high output and ductility with low cost. Filaments are manufactured in a variety of shapes, depending on the end use of the lamp. Usually it's either a coil or a coiled coil. Coiling improves efficiency by helping retain heat in the filament. If a coil stays hot, it needs less electricity to keep glowing. Lead-in wires supply electricity to the filament. They incorporate a fuse at the bottom to protect the lamp from overwattaging in case the lamp arcs. A mount structure supports the filament so that it will maintain its proper shape. A stem press provides an airtight seal around the lead-in wires, and the exhaust tube is used for evacuating the air from the lamp and refilling it with the proper gases. All around this structure, the bulb, made of either hard or soft glass, depending on the final use for the lamp, provides the proper atmosphere for the filament and seals it from the outside air. During manufacture, the air is sucked out through the exhaust tube and replaced with a fill gas, which prevents rapid deterioration of the filament. It's an inert gas, usually argon, although nitrogen or krypton may be used in energy-saving lamps. In small, low-wattage lamps, the bulb may be a vacuum. The final step is the basing of the lamp. The base provides a secure connection to the electric supply, most commonly through a screw-in design. The base also supports the entire lamp and places it in the proper burning position if necessary. Bases are usually made of aluminum, brass, or nickel-plated brass. Today, the manufacture of incandescent lamps is almost fully automated, and in modern production facilities, a number of quality control procedures are used to assure that only the highest quality lamps are produced. Now that we've examined a typical lamp, let's look at some others. The C, or cone shape, is commonly used in small, low-wattage lamps. The S shape is also used for low-wattage lamps, the type found in signs and marquees. The F shape, also called the flame or candle shape, is used for low and medium wattage lamps with a decorative purpose. The G shape is also used for decorative purposes. It's sometimes called the globe or round shape. Of course, the most familiar shape of all is the A line we examined, also known as the GLS shape, for general lighting service. Then there is this recent variation, the mushroom-shaped lamp, used for general lighting and in conjunction with a silvered reflector. There are several lamps designed as directional light sources that have reflectors built right in. For example, the R, or reflector lamp, incorporates an internal illuminized reflector to project the light from the lamp in one direction. A refinement of the R shape is the ER shape, or ellipsoidal reflector. It concentrates more of the light into a smaller beam for special applications. Finally, the PAR, or parabolic illuminized reflector. This directional light source is used both indoors and outdoors and offers a variety of beam angles. The construction of a lamp determines both the amount and direction of the light it produces, but it can also affect the quality of the light itself. Clear lamps produce the highest output per watt, but the light can be very harsh. That problem is solved when the bulb is frosted inside. Etched with acid, the glass is made translucent with only about a 3% loss of light. So soft white or white satin lamps provide almost as much light as a clear bulb, but are much easier on the eyes. Colored lamps are created in a variety of ways. The simplest are the yellow and pink lights, just an A-line lamp with a colored inside coating. Colored PAR lamps use a silicone-based paint and come in different colors. In some cases, colored glass is also used, depending on the application of the lamp. Some lamps also have a silvered or aluminized reflective area used to shine the light in a single direction, to shield the filament from view, or simply as decoration. The seemingly endless combinations of shapes, colors, and designs, the incredible variety of lamps now available, these things ensure that wherever there is a need for lighting, whether general or highly specialized, there is a lamp designed to fill that particular need. So far, we've seen how all these incandescent lamps work and why they're constructed the way that they are. But the critical test of any lamp is how well it performs once the customer actually puts it to use. Let's take a look at some of the operating principles and how they affect the lamp's performance. As we've already seen, light is produced when electricity heats the filament to a glowing or incandescent state. The filament is very sensitive to the amount of voltage being supplied. When the lamp operates at its rated voltage, both its lifespan and its lumen output are at 100% of their values. Increase the voltage over the lamp's rating, and the lumen output increases while the life decreases. For example, a 5% increase in voltage gives you an 18% increase in light output, but it reduces the lamp's life by almost half. Reducing the voltage reduces the light output and extends the life of the lamp. A 5% reduction in voltage produces 12% less light, but nearly doubles the life of the lamp. Life ratings are determined by burning a number of lamps until they fail and keeping track of how many hours they burned. The life rating is an average based on the point where 50% of the lamps have failed. So any single lamp may last longer or shorter than the life rating. It's also important that a lamp not receive too high a voltage too rapidly. Lamps operated on circuits with other high-voltage equipment may be damaged by voltage spikes. We've already discussed how the shape of a filament affects the efficiency of the lamp. Well, both the filament and its support can affect the lamp's durability as well. The supports for the coil are dictated by the end use for the lamp. The more support used, the more it touches the coil. That reduces efficiency because it cools the areas that it touches. So in creating a support, we try to combine durability with the highest possible efficiency. The CC8 is the most common filament shape for A-line or GLS lamps. The coil is held vertically, and it may also have a center support. The C17 filament is used in rough service lamps. The filament is heavily supported and strung to prevent filament shorts due to bumps and knocks. The C9 filament is designed for vibration service on machinery, where a lamp may be subjected to high oscillation. The C7A filament is used in lower wattage lamps. And, of course, there are many other filament styles and shapes, each with its own particular purpose. These filaments and supports are important, but there's another factor involved in determining the life and performance of a lamp: the inert gases that fill the lamp envelopes. The original incandescent lamps, like this one, used a vacuum. But a vacuum can be hard to maintain, and it doesn't provide the longest life. Today's lamps use a variety of gases, all of them inert so they don't react under heat with the tungsten filament. These gases introduce pressure into the lamp and help retard evaporation of the filament. At first, nitrogen was used, but now argon is more common. It has the same properties as nitrogen, but it's less expensive. Many lamps use a combination of nitrogen and argon. Recently, krypton gas has been used to increase lumen output without shortening the lamp's life. But it's more expensive, so it's only used where its advantages outweigh the cost. In our fast-paced, technologically advanced world, where would you expect to find such an old and venerable institution as the incandescent lamp? In our homes, incandescent lamps are used for reading and general lighting. Lamps may be used to set a mood or for setting to work. But the applications for incandescent lighting don't end at home. Incandescent lamps can provide general lighting from hard-to-reach areas. And if they're of a higher voltage than the line voltage, they'll last longer and save the labor required to replace them. Hotels have found that voltage-overrated A-line lamps offer cost savings. Decor-type incandescent lamps come in a variety of shapes, sizes, and wattages for almost any purpose. The variety of lamps available allows designers a wide choice of applications, and for specific purposes, there are lamps in special shapes. The R, or reflector lamp, is the lowest cost alternative in directional light sources. The R lamp is especially useful as a ceiling light. By directing its light downward, it eliminates the need for a reflector in the lighting fixture, which keeps the cost of the fixture down. But it can also be used wherever there's a need for a low-cost, directional light source. The ER lamp, or ellipsoidal reflector, was developed for very special applications. The special optics of the ER lamp create a crossover of light just in front of the lamp. This allows a designer to create a fixture with an opening smaller than the diameter of the lamp. The lamp can then provide full output while the fixture shields it and prevents glaring. By far the most useful directional incandescent light source of all is the PAR. A PAR is made from two pieces of glass, the reflector and the front lens. The reflector is a parabola which has the filament at its focal point. The reflector focuses light directly toward the lens. Lenses are available in a variety of patterns to provide different beam angles, varying from 10 to over 40 degrees. When you consider how much lamp to subject distances can vary, you can see why PAR lamps are so useful. A very close subject may require a wide beam angle for maximum coverage without overpowering intensity. Or, to spotlight a particular display or item, you might need a narrow beam angle. The selection of wattages and beam angles among PAR lamps allows for almost any combination of intensity and coverage. And with the proper fixtures, they can be used both indoors and outdoors. Larger versions of the PAR lamps are made for larger lighting jobs. They are available in 120 volts up to 1,000 watts. A recent development in PAR lamps is the 12-volt PAR 36. The PAR 36 operates at low voltage. This allows it to be used worldwide in conjunction with a transformer, which steps down the high line voltage to 12 volts. Low voltage lamps have several clear advantages. For example, the small size of the filament allows precise control of the light produced by a directional incandescent source. Low voltage sources are also more efficient. They require less wattage for an equivalent amount of light. The Par 36 lamp is available in 3 beam angles and 7 different colors, making this lamp one of the most versatile tools that any lighting designer could hope for. It's appropriate that we now discuss the most advanced incandescent lamp of all, the tungsten halogen lamp. As an incandescent lamp ages, the heat of the filament causes tungsten atoms to evaporate. The tungsten atoms deposit themselves on the bulb wall, which is much colder than the filament. When enough tungsten has evaporated and the filament becomes too thin, the tungsten wire breaks and the lamp fails. A tungsten halogen lamp uses a chemical reaction known as the halogen cycle. Halogens, elements such as chlorine, iodine, and bromine, have particular properties. In a tungsten halogen lamp, a small percentage of halogen gas is added to the fill gas. The most commonly used is bromine, since it doesn't color the light produced by the lamp. When the lamp is turned on, the tungsten atoms that evaporate from the filament combine with the halogen gas instead of depositing themselves on the glass envelope. The combined elements travel through the convection of gases in the envelope until the tungsten redeposits itself on the filament. The result is a lamp which remains clear and unblackened throughout its life. And thanks to the lamp's design and operating principles, there are some additional benefits. First, there's the small size in relation to the wattage. A tungsten halogen lamp requires a much smaller envelope than a normal incandescent lamp. This smaller envelope is also useful because it helps keep the lamp temperature up. That's important since the halogen cycle requires the temperature of the bulb wall to be at least 250 degrees centigrade. That's much hotter than a normal incandescent lamp, and the bulb has to be manufactured of quartz glass to withstand the temperature. Another benefit of the tungsten halogen lamp is that it maintains its lumen output over its entire life. A normal incandescent lamp loses light output due to blackening, but the cleaning process of the halogen cycle ensures a steady output with a tungsten halogen lamp. The quality of light from a halogen lamp is also different. Most tungsten halogen lamps are designed to burn at approximately 3,000 degrees Kelvin. That's right about here, somewhat higher than normal incandescent lamps, which means that the light is whiter. One of the first applications for tungsten halogen lamps was for area and architectural lighting. But as you might imagine, they found their way into a wide variety of uses, from theaters and studios to headlights. There are many different types of these lamps available. This linear type is most common. Contact with electrical power is made through pressure contacts at either end of the lamp. Another type is the 2-pin base. This single-ended lamp allows for much more compact fixture designs for both indoor and outdoor use. It's important to note a tungsten halogen lamp should never be touched with your bare hands. Skin oils can contaminate the high-purity quartz and will reduce lamp life. One recent innovation is the MR16, or True Aim lamp. The MR16 consists of a small tungsten halogen capsule in 20 to 75 watts, mounted in a multifaceted reflector. The reflector is made of glass coated with dichroic reflective material. The dichroic coating consists of multiple layers which reflect visible light but allow infrared light to escape through the back of the lamp. The result? A very directional light which contains less heat than a lamp with an aluminized reflector. In 1987, Sylvania Europe developed the True Aim Professional. The Professional series adds a front lens which both protects the lamp from contamination and provides protection in case of lamp failure. Yet another exciting innovation is the capsule light, designed for use on 120-volt systems. The capsule light uses a tungsten halogen capsule inside a lamp housing to provide both a crisp white light and a long life. It's a terrific example of how tungsten halogen technology is spreading more and more into everyday light sources. That's an overview of the world of incandescent lamps. Next to the sun, the most dependable light source on Earth. Remember, Sylvania takes pride in its product. We always strive to be the best, and we know that you do too. Hello and welcome to the second in our series of GTE Sylvania International Video Training Seminars. These seminars are designed to acquaint you with the world of lighting and to give you a basic understanding of one of the most important tools in modern life, the electric light. In our first seminar, we discussed the original electric light source, the incandescent lamp. Now let's move on to the next generation of lighting, fluorescent. The invention of the incandescent lamp was a revolution in our society. But it came with some problems of its own. The incandescent lamp uses only about 6% of its power to produce light, while 81% of its power is converted to heat. Naturally, a search began for more efficient light sources, and in 1938, the first practical fluorescent lamp was introduced in the United States by the high-grade Sylvania Corporation, a predecessor of our current GTE Sylvania. Then, as now, the basic component of the fluorescent lamp was a glass tube. The diameter and length of the tube vary depending on the wattage and design of the lamp. The inside of the tube is coated with very pure crystalline phosphor compounds. Various mixtures of these compounds are used to determine the color of the light produced by the lamp. Glass end caps are then added, each containing an exhaust tube, which is used to remove the air and fill the lamp with an inert gas and a minute amount of mercury. The end caps also hold lead-in wires which supply electricity to the cathode. The cathode is a coiled electrode which is coated with an emissive material composed of barium, strontium, and calcium oxide. The end caps are sealed into the ends of the glass tube, and after the exhaust process are covered with metal bases which provide support and electrical connections for the lamp. The electric supply to the lamp is regulated by a ballast, an external device that limits the current yet provides the necessary starting power to initiate the light-producing action. There are two categories of fluorescent lamps, cold cathode lamps and hot cathode lamps. Almost all fluorescents used today are hot cathode due to its higher efficiency. In order to understand the creation of fluorescent light, it's necessary to examine activity at the atomic level. The process begins with the flow of electric current through the cathodes. As the cathodes heat up, their special coatings begin to emit electrons. The voltage applied between the electrodes by turning the lamp on creates an electrical field, and the electrons accelerate down the tube towards the opposite electrode. As they travel through the tube, the electrons collide with the electrons orbiting the mercury atoms, which can be knocked free of their orbits to become new free electrons, or excited in their orbits, absorbing kinetic energy from the collision. The freed electrons accelerate down the tube, striking other mercury atoms. And as the chain reaction process continues, it becomes an arc discharge extending through the tube. The excited electrons, however, still captive, release their extra energy as ultraviolet radiation as they relax back into their orbits. This invisible short wavelength radiation strikes the phosphors in the tube coating, which absorb the energy and re-radiate it as longer wavelength visible light in a reaction known as fluorescence. The color of the light is determined by the type of phosphors used and the wavelengths at which they re-radiate the ultraviolet energy. Fluorescent lamps, as with all arc discharge lamps, must be operated with ballasts, which control the lamp current and provide the required starting voltages. As the current in the arc increases, the resistance decreases, and if unregulated, the lamp would draw so much current that it would burn itself out. Fluorescent lamps are much more efficient than incandescent lamps. While an incandescent lamp produces approximately 12 lumens per watt, a fluorescent lamp produces anywhere from 60 to over 100 lumens per watt. For example, a 40-watt incandescent lamp produces about 460 total lumens of light, while a 40-watt fluorescent lamp produces 3,150. Over 4 times the light is created by fluorescent lamps for the same wattage. Since 1938, Sylvania has remained an innovator and leader in fluorescent lighting, constantly refining and improving its fluorescent lamps and adapting them to new uses. Today, fluorescent lighting accounts for a major percentage of all lighting used around the world. Because the characteristics of fluorescent light are very different compared to incandescent light, it's important to understand how their colors are measured and compared. As discussed in our first program, one color quality of a light source is its color temperature and is measured in degrees Kelvin. But color temperature is not an absolute and is not the only measure of color. Color temperature is measured for a light source by comparing its radiation with that produced by a theoretical substance called a blackbody. This theoretical blackbody completely absorbs any light that falls on it. But don't confuse this with a black hole of space, whose gravity is so strong it won't even release light. A blackbody is simply a mathematical concept, a something that reflects absolutely no light. When heated, however, the motions of its electrons begin to emit radiation and will emit the maximum amount of energy possible in every frequency possible according to the laws of physics for the temperature to which it is heated. In the real world, a tungsten filament closely approximates the characteristics of a blackbody. Of course, as the blackbody is theoretical, its radiation at different temperatures is derived through a mathematical formula, which was developed by Max Planck, a German physicist, in 1900. The color temperature of every incandescent source of light is assigned by comparing its radiation to that of the theoretical blackbody. The temperature of the blackbody, where its light most closely matches the light source, is then used to designate the color temperature of the source. The actual temperature of the filament, however, is not necessarily the same as the color temperature of the lamp. A key point, though, especially with respect to fluorescent light, is that a blackbody is a continuous spectrum radiator, while fluorescent light does not radiate a continuous spectrum. Any light source can be defined by its SPD, or spectral power distribution graph. An SPD is an analysis of the energy levels at different wavelengths for a light source. For example, a blackbody at 2000 degrees Kelvin would have a smooth curve with most of its energy concentrated in the invisible infrared and visible red regions. As the temperature of the blackbody is raised, more and more energy is shifted into the visible spectrum and includes more blue. But the single arc remains, indicating that broad bands of wavelengths are represented. Since only visible wavelengths affect the colors, SPDs don't normally include non-visible radiation. When applied to fluorescence, the spectral distribution reveals the different nature of its light. In other words, not all wavelengths of light are strongly represented by the phosphors in a normal fluorescent lamp. In fact, some visible frequencies are absent, while others are very strong. This is the SPD of a warm white fluorescent lamp, showing high relative energy in yellow and orange, and very low energy in blue and red, and even a dip in the green between blue and yellow. Both the color and intensity of the light depend on the mixture of phosphors coating the inside of the fluorescent tube. The spikes in the graph are the spectral lines of mercury, indicating visible light emitted at those wavelengths as a result of the collisions between the electrons in the fluorescent tube. Because of the special characteristics of light sources such as fluorescence, a system called correlated color temperature, or CCT, has been developed in order to classify them. Under this system, a fluorescent lamp designated as 3000 degrees CCT will approximate the appearance of an incandescent lamp designated as 3000 degrees Kelvin. If measured by instruments, one could see that they were not, in fact, the same. But the correlated color temperature is based on the sensitivity of the human eye and the effort of the brain to perceive nearly white sources as white. Correlated color temperature gives you the ability to describe a fluorescent lamp in terms of warm or cool appearance. However, it does not define how a lamp will make colors appear. To further define the color of a lamp, another measurement must also be used to describe the quality of light, and that's Color Rendering Index, or CRI. This index describes the ability of a light source based on its SPD to truly render the actual colors of an object. We've all noticed that colors, such as the colors of our clothing, can look different outdoors than they do indoors. For example, a dark blue suit may look black under the incandescent lights of a store, but when examined in the light of day, will show it's blue. This is because normal incandescent lamps are weaker in the blue spectrum, concentrating more of their energy in red and yellow. If there is too small a blue component of light, then it will not be reflected for us to see. This is a common illustration of the color rendering index. CRI is based on a scale of 100, where the higher the rating, the better the ability of the lamp to render colors that are true and natural. As fluorescent lamps are manufactured with different phosphor combinations, they have different SPDs, CCTs, and CRIs. This is the SPD of a cool white fluorescent lamp. The energy is plotted against the colors of the visible spectrum. As you can see, cool white contains a very large relative energy in blue, green, and yellow, and is somewhat weaker in orange, with a sharp drop-off in red. It is rated at 62 CRI, with a correlated color temperature of 4200 degrees Kelvin. When we look at the SPD of an incandescent fluorescent lamp, rated at 2700 K, we see that the spectrum is shifted to the warmer colors, yellow and orange. A smaller component of blue and green is present. The incandescent fluorescent has a CRI of 90. Daylight color fluorescents have a CCT of 6300 K and a CRI of 73 to approximate natural daylight. It's important that you do not use CRI to compare light sources of two different color temperatures. This does not properly judge the suitability of a light source for a job. To do that, you must consider the overall needs of the area to be lighted. The simple key to CRI is that when two light sources of equal correlated color temperature are compared, the one with the higher CRI value will render colors more visually pleasing and true to life. Sylvania spends a great deal of time and money improving the fluorescent lamp, developing new phosphor combinations which will produce desirable colors with high CRI ratings, and seeking more efficient phosphors which will provide more light for an equal amount of electricity. Let's take a look at some of the types of construction that have been developed over the years. There are three basic types of fluorescent lamps: preheat, instant start, and rapid start. The original fluorescent lamps introduced in 1938 were preheat lamps. They required heating of the coils through starter circuits before the lamps would start. Preheat lamps are still very common and are used most in Europe and other high-voltage areas. They're available in lengths up to 60 inches. The second generation of fluorescent lamps was introduced in 1944. The slimline, or instant start lamps, were developed to eliminate the slow starting associated with preheat lamps. The slimline instant start lamps require no starters. They use full power to start the lamp, so they need a much simpler ballast system and require less maintenance than a preheat lamp. In 1952 came the introduction of the rapid start lamp. Today, the rapid starts are one of the most commonly used fluorescents. The rapid start fluorescent product line also includes the high output, or HO lamps, and the very high output, or VHO lamps. These use higher currents in order to increase efficiency. They both require special construction to allow for these higher operating currents and pressures, as well as specially designed ballasts to deliver the proper higher voltages. The ballast is an extremely important element in the operation of any fluorescent lamp. The most common ballast is the inductance type, which uses a magnetic choke coil to limit the current supplied to the lamp. This circuit diagram shows a very simple ballast system for a preheat manual starting fluorescent lamp. Power is applied to both ends of the lamp. One switch controls the current through the starter circuit, while an on-off switch controls the use of the lamp. When the starter button is pushed, both switches close, completing the circuit. As the current passes through the cathodes, they heat up and begin to emit electrons. After about a second, the starter button is released and the circuit is broken, resulting in a voltage spike which initiates an arc discharge between the cathodes, and the lamp starts. Pressing the off button opens the on-off switch and stops the current. More common than the manual starter for preheat circuits is the automatic starter. In this case, an on-off switch controls the use of the lamp, and either a glow switch or a thermal switch controls the starter circuit. Both starters incorporate a bimetal switch which is activated by heat to control opening and closing. For example, the thermal switch is in the closed position when the lamp is off. When the lamp is turned on, current flows through the starter to heat the cathodes. At the same time, the electricity heats the bimetal switch, causing it to expand and break contact. The process then continues as with the manual system. One disadvantage of automatic preheat lamps is that when they reach the end of their lives, their starters continue to try to start them until the starter fails or the lamp is replaced. Starters with automatic cutoffs have been designed to prevent this. The manual reset starter uses a second bimetal switch which opens after the starter is unable to start the lamp. Every time the starter cuts out, the reset button must be pushed to reactivate it. The best solution, an automatic reset starter. The automatic reset starter uses a second heater which holds the contacts open as long as voltage is supplied to the lamp. In the case of a failed lamp, the starter will not continue to try to start the lamp. Instant start slimline lamps were created to eliminate the need for starters. They use the ballast to provide high voltage at one end of the lamp and normal voltage at the other. Since only one connection is required at the end, single-pin bases are used. Due to the presence of high voltage, special lamp holders are used to prevent shock hazards. The most common fluorescent lamp, the rapid start, uses separate windings within the ballast to provide coil heating. Once these coils have started the lamps, they continue to glow from the small amount of current supplied to them, but this doesn't affect the performance of the lamps. Ballast selection is based on several factors. For example, all inductance or magnetic ballasts create noise, a hum. So most manufacturers will have different classes of ballasts depending on the amount of noise created. But there are other factors to consider besides noise. The increased awareness of energy consumption has led to the introduction of more energy-efficient ballasts. These are designed to save electricity by reducing losses within the ballast. Used in conjunction with energy-saving lamps, these ballasts can result in significant savings. The most energy-efficient ballasts are the electronic ballasts. These ballasts operate the lamp at higher frequencies than magnetic ballasts. They not only save energy, but they also improve lamp efficiency. It's important that the proper type of ballast be used with each of the 3 types of fluorescent lamps. The only exceptions to this rule are the rapid start lamps, which will operate correctly on preheat ballast systems. Otherwise, the lamps and ballast must be properly matched. When calculating the power consumption of a system, the energy used by the ballast must be included. The lamp wattage plus the ballast wattage make up the total power used by a fluorescent lighting system. The versatility of the fluorescent lamp has enabled manufacturers to create a variety of shapes and sizes for a number of different uses. Obviously, the most common is the straight tube, used singly or in combination with others. The circline lamp is simply a straight fluorescent tube bent into a circle. It can be used where size limitations prevent the use of a straight tube of similar wattage. One circline can also be nested inside another for greater output. The curvalume, or U-bend lamp, is similar to the circline. A standard 40-watt lamp is bent into a U-shape to allow for smaller, more compact fixtures and spaces. A recent innovation is the GLAMx, or compact fluorescent lamp. The compact fluorescent is a single-ended lamp made with a bent tube. It's available in a single tube and in a double tube configuration. By using an adapter which contains the ballast, these lamps can directly replace incandescent lamps. With their screw-tight bases, these adapters are a quick and easy way to convert existing incandescent fixtures to fluorescent. Additionally, the compact fluorescent is finding many new applications in fixtures designed especially for this lamp. 2 very specialized fluorescent lamps, the reflector lamp and the aperture lamp, are used for many functions. The reflector lamp has a partial internal reflective coating, which provides directional control. Reflector lamps are useful where space is limited or in areas that are difficult to clean. The light is focused in one direction and eliminates the need for a separate reflector, which may become soiled. The aperture lamp has a clear window which runs the length of the lamp. This window is very bright, and when used with reflectors and lenses, can provide highly concentrated light useful for applications such as bridge lighting or lighting signs. So far, we've explored the basic concept of fluorescent lighting, as well as some of the varieties and styles available. Compared to an incandescent lamp, a fluorescent lamp has a very long life. In fact, the average life of fluorescent lamps can range from 6,000 to over 20,000 hours. The life of a fluorescent lamp is usually determined by the number of starts, that is, by how many times it is turned on and off. The end of life normally comes when there is no longer sufficient emissive material on the electrode coils to start the lamp. Measurement of fluorescent lamp life is calculated using a 3-hour cycle, which means the lamp is in use for an average of 3 hours every time it's turned on. If the length of these cycles is extended, life can be significantly increased. For example, a standard 40-watt fluorescent lamp is rated at 20,000 hours average life when using the 3-hour cycle. Extend the cycle to 10 hours, and the life rating is increased to over 27,000 hours. Burning lamps continuously would result in an average life of over 37,000 hours. Half would burn for a shorter time and half longer. Another important factor in fluorescent lighting is lumen maintenance. As a fluorescent lamp is used, its ability to produce light diminishes due to deterioration of the phosphor coating and blackening of the inside of the lamp caused by emissive material from the electrodes. The blackening is especially noticeable at the ends of the lamp. A lamp emits more lumens than rated during its first 100 hours of use, so measurements of lumen ratings are based on the 100-hour point. As the lamp ages, the lumen output slowly decreases until the end of the lamp's life. Not all lamps decrease at the same rate. Some phosphors are better than others, but all lamps do decline in light output with use. Temperature also has a direct effect on the performance of fluorescent lamps. Lumen ratings are based on an ambient or surrounding temperature of 25 degrees centigrade or 77 degrees Fahrenheit. As the temperature exceeds or falls below this point, light output begins to decrease. 77 degrees Fahrenheit would be uncomfortably warm for most areas, but the heat generated by the lamp and its surrounding fixture is usually enough to keep the bulb wall at the proper temperature and to make the lamp operate properly even when temperatures are well below 77 degrees. Sometimes, though, it's difficult to maintain the proper temperature to operate the lamp correctly. In these cases, the selection of the proper lamp and ballast can overcome the problem. Occasionally, humidity can cause rapid start and instant start lamps to be hard to start. To combat this, a thin coating of silicone is applied to the lamps to aid starting. Because of their higher starting voltage, preheat lamps usually don't have this problem. Fluorescent lamps are not as sensitive to voltage changes as incandescent lamps. However, increases and decreases in voltage will reduce efficiency and life. Reductions in voltage due to long wire leads or other equipment on the same line can lead to shorter lamp life, early blackening of the ends, and eventual failure of the lamp. Let's return to the subject of color and talk about that in even greater detail. A surprising number of colors are available for a variety of uses. These colors are based on different mixtures of phosphors, and each has its own particular use. The human eye is the most important tool for determining precise color. The eye's capacity for change and adaptation is nothing short of miraculous. The human eye is most responsive in light which is centered in the yellow range. However, the eye adapts itself to whites as white under different color light sources as long as other colors are present as some percentage of the light. A simple illustration we've all seen is in auto headlights. At night, when they're the only source of light, they appear to be a nice white color. But in the daytime, they are a dull yellowish color compared to normal daylight. Fluorescent lamp colors are perceived in the same way by the eye. If a fluorescent is the only source of light in use, the eye adapts to that source and calls it white. As long as some component of other colors is also in the light, we have a useful general lighting source. Therefore, the selection of colors for fluorescent lamps should be based on what a designer is trying to accomplish in creating an atmosphere for the area to be lighted. When fluorescent colors are created, several factors must be considered. First, the overall efficiency of the phosphors, which must produce sufficient light for the amount of power used. Next, the color temperature. The phosphors must produce the right color temperature in order to achieve the level of coolness or warmth desired. Lastly, the color rendering index, or CRI, must be high enough to produce a good representation of all colors. This is vital, since the human eye must perceive the colors of fluorescent light as white. Different phosphors are mixed to obtain the correct properties for each color of lamp. The inside of each fluorescent tube is then coated with these phosphors. A new development is the use of double coat technology. Double coating allows the economic use of expensive rare earth phosphors, which complement the wavelengths produced by normal fluorescent lamps, resulting in excellent efficiency and a high CRI. Now, we've only touched on the vast subject of fluorescent lamps. You'll have to be familiar with the wide variety of fluorescent lighting products and all their many characteristics. That takes a lot of expertise and a lot of experience. GTE Sylvania hopes that you have found this seminar to be a good first step toward mastering the field of fluorescent lighting.